Hello. In this video, we're going to look at another application of prime factorization, and that is for working with perfect squares and perfect cubes. Before we do, this is a table with some really helpful powers to know. It's helpful to know the first few powers of 2. I've listed here up to 2 to the power of 6, but if you know more than that, that's also really helpful. Just to recognize, if I see the number 64, that's a power of 2. If I see the number 32, that's a power of 2. Same thing for the first few powers of 3, 4, and 5. First couple powers of 6. And then it's also really helpful to know the square numbers up to 20. So to recognize, and you may forget 1 or 2 of these in here. Maybe you forget that 17 squared is 289, but if you remember that 16 squared is 256, that will still be helpful. But these are some squares and cubes that are helpful to know. One of the things they're helpful for is when we have to estimate the value of numbers that are not perfect squares or cubes or whatever they are. So for example, if I'm asked to estimate the value of 130, I can consider the square numbers that I do know. So the square root of 130 has to be somewhere between the square root of 121 and the square root of 144. So I know from this that the value of this must be between 11 and 12. Now, it's probably not super far off from either one. I would probably estimate it to be 11.4, 11.5, somewhere in there. Obviously, if I need a more specific or more precise measurement, there are some ways I could guess and check. I might try 11.4, for example, and actually multiply them together and see if I get something bigger or smaller than 130 and go from there. If I guessed 11.5, I would get something a little too big. It actually is much closer to 11.4 than 11.5. But if I was just making a rough estimate, I wouldn't necessarily know that, but that's still good enough for a lot of applications, just to know it's about 11 and a half. I can also use prime factorization to decide if things are perfect squares, perfect cubes, both, neither. Maybe I can figure out if it's a power of 6 or whatever. And prime factorization allows me to do that because if the factors are squares, then the number is a square. If I have cube factors, if all my factors are perfect cubes, then the number itself is a perfect cube. So let's consider what would happen if I divide these out. Now, I'm going to start by, in this case, not just using prime factors, because I know I am looking for squares or cubes. So I'm going to divide by things that are a little bigger. So for example, when I look at 13,824, I know 24 is divisible by 4, perfect square. So this is also going to be divisible by 4. 13 divided by 4 gives me 3 with 1 left over. 18 divided by 4 gives me 4 with 2 left over. Then I've got 5 with 2 left over and 6. So 13,824 divided by 4 gives me 3,456, which is again divisible by 4 because I know that 56 is divisible by 4. So doing that, I get 864, still divisible by 4. So I'm going to keep going as long as I can. Why not? I get 216. 216 is one of the powers that I recognize. 216 is 6 cubed. So at this point, I can say, well, that is 6 times 6 times 6. Notice none of these are prime factors. So I'm actually going to go a little bit further and divide these into primes. But that's pretty quick once I'm down to numbers like 4 and 6. So what I have at the end, if I count up how many 2's I have, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is 2 to the power of 9. And I have 3 to the power of 3. So notice the exponents now. 2 to the power of 9 is not an even number of 2's. In other words, I can't pair up the factors of 2. I can have a pair, a pair, a pair, a pair, but then I've got an extra. And a pair of 3's, but an extra. So this is not a square. It is, however, a cube because I actually can divide the factors nicely into groups of 3. So 3 2's, 3 2's. I've got my 3 2's here, and I've got my 3 3's. So everything fits into nice groups of 3's. That means they're all perfect cubes. Looking at the exponents, this can be divided by 3, the 9 can, and the 3 can be divided by 3. That makes this a perfect cube, but not a perfect square. 176,400, well, I can see that that's obviously divisible by 100, so I'm going to start there. So I've got 100 times 1764. 64 is divisible by 4, so I know I can divide this by 4. And when I do, I get 441. 441 is another one of the numbers that I recognize. So 441 shows up. Oh, it's actually not on my list because it's the next one right after it. 441 is 21 times 21. If you didn't recognize that, it is divisible by 3. You can divide it by 3. It's divisible by 9. You could divide it by 9. You could go that way. But I'm going to go this way because what that has shown me is I actually don't have to necessarily go all the way down to primes to see that this is a perfect square. Because what I can see at this stage is I have 10 times 10, 2 times 2, 21 times 21. So this is in fact a perfect square because one way it could be written is as 10 squared times 2 squared times 21 squared. Everything is squared, so this is a square. That's not really enough to know yet if it is a cube as well, because it certainly could be both. So what I'm going to do is I'm actually going to break these down further just to show that I can't also divide it into groups of 3. So all the way down to prime factors, what I now have is 2 times 5, 2 times 5, 3 times 7, 3 times 7, which means as prime factors overall, I have 1, 2, 3, 4 2s. That's an even power, but it's not divisible by 3. I have 2 3s. Again, even, but not divisible by 3. I have 2 5s, and I have 2 7s. So all of these exponents are divisible by 2, which makes it a perfect square, but they're not divisible by 3, so it is not a perfect cube. 1125, just kind of carrying on with the same idea, I can divide it by 25, noticing that it ends in a 25. So 1125 divided by 25 gives me 45. That is 5 times 5 and 5 times 9, which is 3 times 3. What I've got in this case is 3 squared times 5 cubed. The 3 squared is a perfect square. That exponent is divisible by 2. And 5 cubed is a perfect cube, but they're not both even, and they're not both divisible by 3. So in this particular case, the whole number is neither a square nor a cube, because it has one square factor, 3 squared, and one cube factor, 5 cubed, but it needs to be completely squares to be a perfect square and completely cubes to be a perfect cube. So in this last case, 853776, it is divisible by 4. Actually, I'm going to go ahead and divide it by 16, just because I happen to know it is divisible by 16. That gives me 53361. If you divided it by 4, you would then notice it's divisible by 4 again. In this particular case, I can divide it by 9, which gives me 5929. I believe it is divisible by 49 at this stage, yes. And then that gives me 121, which is one of the powers I recognize. 121 is 11 times 11. So this gives me 16 as I recognize a power of 2. That is 2 to the power 4. 9 is 3 times 3. This is 7 times 7. So we end up with, as a final, 2 to the power 4 times 3 squared times 7 squared times 11 squared. So this one again is going to end up being a perfect square because all of my powers are even. Now it is possible for the number to be both a perfect square and a perfect cube if they are both even and divisible by 3. In other words, if all the powers are multiples of 6. But in this case, that is not the case, so we just have squares. If I wanted to know what its square root was, the square root of 853776 is the square root of 2 to the power 4 times 3 squared times 7 squared times 11 squared. Well, the square root of 2 to the power 4 is 2 squared. Square root of 3 squared is 3. Square root of 7 squared is 7. Square root of 11 squared is 11. So the square root of this number is 4 times 3 times 7 times 11, or 924. So this is a way of determining a square root or cubed root without having to do quite a lot of calculations, just using prime numbers.